So in this video we're going to look at some questions from the mathematics admissions test. Some of you will know that that's the test that you need to sit if you're thinking of applying to Oxford University to study maths or some of the related programs, maths and philosophy, maths and stats, maths and computer science and philosophy. It's also used by Imperial, and so it's a tough exam. But it's sat towards the start of year 13 in November usually, so it doesn't require as much advanced content as, say, the STEP exams if you've looked at any of those. There's more of a focus on sort of quite tough problem solving, but with just like AS maths content mainly. So there's a combination of short questions and long questions, and in this video I'm going to look at some of the short questions. So it tells you on the front, depending which courses you're applying, which ones you have to do, but everyone who sits the paper has to do these short questions, and they're multiple choice questions. So working doesn't matter for these. We've just got to get the answer any way we can, and we might do that by a combination of either actually getting directly to the answers or possibly in some cases eliminating some of the possibilities. They used to only put 4 options in, they've now put 5 options in, which makes it a bit harder to do that, but in some cases it's still possible. So we'll have a look at that. Okay, so question A, a sequence has first term 1 and subsequent terms are defined by an plus 1 equals L times an for n greater than or equal to 1. What's the product of the first 15 terms of the sequence? Now, so we should recognize that this sets up a geometric progression. If we have a1 equals 1, then a2, by the definition here, would be L times a1, so it would be L, and then a3 would be L squared, a4 would be L cubed, etc. And but we've got to be careful. It says what's the product of the first 15 terms. So we know we've got formulae for the sum of the first 15 terms, but actually here it wants a product of the terms in this geometric progression. So it's going to be a1 times a2 all the way up to a15. So that's going to be 1 times L squared. And the final term here, a15, is not actually going to be L to the 15, but L to the 14. The index is always 1 lower than the term number here. And so actually, by the rules of indices, we know this is just then L to the power of 1 plus 2 plus 3, etc., all the way up to 14. So actually the relevant result here is not really about geometric progressions, but about arithmetic progressions. You could probably just add this up fairly quickly in your head, but you could also use the formula for the sum of the arithmetic progression here, which has got 14 terms in it, because remember that first one didn't contribute anything. So just adding up the numbers from 1 to the 14. So you can do a half times the first term plus the last term, which is 1 plus 14 multiplied by the number of terms. Should be familiar from AS Maths, so that's L to the 1/2 times 15 times 14, so 7 times 15 here, which is L to the 105, which gives us the answer D. Now I've done that question fully and directly, but you really know we are trying to do these as quickly as possible, so you may also want to have glanced at the answers before we did this question, because actually by the time we've got to this stage we've realized that the answer is just well, in fact even this stage, L to some power, and we've realized we've just got to add these numbers together. Well, if you look at the answers, I mean at this stage this becomes the only reasonable answer, so you may not formally have to actually do the adding up and making sure you get 105. There's nothing close. They haven't given us like 104 and 106 as options, so you may find you can do that without necessarily doing like every step like I've done here to save a bit of time. You don't have that much time here. Probably my guess is probably by the time I do all the videos to go through this whole paper, I may take longer than you have for the paper, because I talk about it as I go along, right? Whereas when you're doing it, you just need to kind of get on with it as quickly as you can. Okay, question B. An irregular hexagon with all sides of equal length is placed inside a square of length 1, as shown below. what is the length of one of the hexagon sides. So the hexagon here is this 1, 2, 3, 4, 5, 6-sided shape. So we don't know the side lengths. In fact, it says it's an irregular hexagon, but it does have sides of equal length. So the angle is not the same, but the lengths are all the same. So that's useful to us. So let's just call it x. Say so that length is x, but this length along here is also going to be x, and x down here as well. Now let's just think about what the consequence here is, because this is a square of side length 1. So if I well, there's different ways of getting here, but certainly this length and this length are the same. So this one is 1 minus x, and this one is 1 minus x here. Perhaps it's easier actually just to call it a, and then we can see how a and x relate. This is a right angled triangle we've got here. So by Pythagoras, 2 times a squared is equal to x squared. So a is going to be x divided by the square root of 2. So the side length here is x plus x divided by the square root of 2, or x times 1 plus 1 over root 2. So that's equal to 1. So I just need to work out what this is and do 1 divided by it. So 1 plus 1 over root 2, that's the same as root 2 plus 1 over root 2. So 1 divided by that is just taking the reciprocal, so I get root 2 over root 2 plus 1, not one of the answers. So we see we need to rationalize this. Again, multiply by root 2 minus 1, top and bottom. Again, that should be a familiar thing to do, to create the difference of two squares on the bottom, which here is root 2 squared minus 1 squared, which is just 1. So in fact, I just get root 2 times root 2 is 2, and root 2 times minus 1 is root 2, so 2 minus root 2, and that is one of the answers here, which is B. Okay, so first two questions are complete. So let's look over the page, and question C says we've got the origin lies inside a circle with equation x squared plus ax plus y squared plus by is equal to c, precisely when one of these conditions holds, and we need to choose which of those conditions it is. So when is the origin inside of this circle? Well, I think you should have studied circles at AS Maths. That is required for this paper, and hopefully if you've studied those enough, you'll have an instinct here, which is to complete the square in both x and y to give the form of the circle, so that it's written where we can see its center and its radius clearly. So completing the square in x here, we've got x squared plus ax, so that gives us x plus a over 2 all squared. That's going to introduce a term a squared over 2 squared, or a squared over 4, which I need to subtract. Same for y. So we've got y plus b over 2 squared minus b squared over 4 equals c. So let's just collect this together. So x plus a over 2 squared plus y plus b over 2 squared equals a squared over 4 plus b squared over 4 plus c. Okay, so we can now see where the center and the radius are, and so we need to know whether the origin lies inside this circle. Okay, so we've got a circle, and the center is minus a over 2 minus b over 2, and we know what the length of the radius is here. Okay, so now where would the origin be? Well, I suppose let's just think about what happens then. So let's say the origin is over here. Okay, It could be anywhere really, but let's put the origin here, and the distance here would be a over 2. Horizontally, the vertical distance here would be b over 2. So, if this length here is smaller than the radius, then the origin would be inside the circle. If this length here is bigger than the radius, it would be outside the circle. So we need to think about, for the origin to be inside the circle, I need a over 2 squared plus b over 2 squared, and then take the square root. That gives me the distance here. That's got to be less than the radius, which is the square root of the right hand side of this equation. But these things are distances, so we're definitely positive things, and I square both sides to get rid of the square root. A over 2 squared is the same thing as, sorry, that should say 4. A over 2 squared is a squared over 4 squared, so subtracting that from both sides, and we just end up with c. C is bigger than 0, which again is one of the answers. So that's the correct conclusion there. Okay. Right, let's have a look at D. How many solutions does cos to the nx plus cos to the 2nx equals 0 have in the range 0 up to 2 pi for an integer n greater than or equal to 1? So my experience teaching A-level maths was that people often didn't like these kind of trig questions where you have to solve equations, but they're not, there's method, that kind of always works for this sort of question. So we look at this and we think, okay, it looks awkward of cos to the n and cos to the 2n, but let's just forget for a second it's cos to the power of nx, and let's just think of it as cos to the power of n means cos x to the n, and cos to the 2nx means cos x to the 2n. Okay, so let's just think of this as something to the power of n, and we'll worry about the fact that it's cos n later. So it's just c to the n plus c to the 2n is equal to 0. Okay, and we can factorize this and get c to the n times 1 plus c to the n equals 0. Okay, so we'd have solutions here. Just like if this was x times 1 plus x equals 0, well, either x is 0 or x is minus 1, so we must have either c to the n is 0 or c to the n is minus 1. Okay, and now actually let's just think about what this means then. So c to the n is equal to 0. Well, that can only happen when c equals 0, whatever the value of n. N is a positive integer, so something to the power of 0 being 0 would mean it would have to be 0. Now something to the power of a number to the power of n is equal to minus 1. Okay, well, this depends on n, right? So if it's like c squared equals minus 1, there are no real solutions. Worth noting, by the way, if you've done complex numbers in further maths, that because they're not in AS, you're not expected to know about them or use them for this paper. So if you think complex numbers are coming up in an answer, I guess there's another, well, maybe that you could use them, but there's probably another way of dealing with it as well. But here, certainly there's no, in this context, this just doesn't work. Whereas if I have an odd power, well, that would, then it does work. I can just take minus 1. Minus 1 cubed is minus 1. Okay, so in this case, and now you look at the answers, and think, oh yeah, there's some different cases for even or odd n, so I think the answer is probably going to be one of these. So here I have that if n is even, this doesn't work, but if n is odd, we can take c equals minus 1. Okay. Now, so what does this really mean? C was cos x, so cos x equals 0. Well, how many times is cos x equal to 0 between 0 and 2 pi? Well, the graph of cos x you should be able to draw very quickly between 0 and 2 pi. So cos x equals 0 once, twice, so we get 2 solutions in all cases. And when n is odd, can we make c equal to minus 1? Yeah, we also get this extra 1 down here. So 2 solutions in all cases, and we get an extra 1, so 3 solutions if n is odd, which gives us the answer here, D. Okay, so I mean, you see what I mean here? We're using the methods of AS level maths, but we're doing it in a much harder problem solving based way. Okay. Right, and E, right, there's always a graph question of something like this, and you know, with these graph questions it's usually fairly easy to eliminate at least 1 or 2 of the answers, but then to actually kind of really come to the conclusion as which one is correct, it is not always so straightforward. So let's have a look. We're told this is the graph of y equals x minus 1 squared minus cosine of pi times x, and we should start by, you know, we're trying to work out which one it is. We'll try and start with the most obvious things we can. So I'd always start by looking and say, okay, what about you know, axis crossing points? So for example, if I take, you know, x equals 0 here, y would be minus 1 squared minus cos of 0. So that should be 1 minus 1, which is 0. Okay, so certainly this graph should pass through the origin. This one does, this one does, this one does, but neither of these two do, so we can immediately rule out D and E as options. Now, to go beyond that, I guess, you know, there may be different, you know, things we can analyze here, but I think let's stick with the axis crossing points, and let's think about the you know, how many solutions does this equation have? So if I want to put y equals 0 here, well, y equals 0 would give us this whole right hand side equals 0, so that's the same as x minus 1 squared is equal to cos of pi x. Okay, now at that point, I think personally I would consider the graphs of these two functions and think about where they intersect. Okay, cos of pi x, okay, and we're in radians here, so cos of pi x is going to look like the graph of, well, it's just the cosine graph, and it's pi x is going to give it a like a squash by a scale factor pi in the x direction. So if you think about it, you know, cos of 1 here is going to be what would usually be cos of pi. So, you know, this would be pi if it was just the ordinary cos graph, so that's now 1. Cos of 2, if I put x equals 2 in here, it would be what, you know, cos of 2 pi. So it's just like counting in, you know, the usual cos graph, but in pi's. So we've got 0, minus 1, etc. Okay. Now what about the other side, x minus 1 squared? Well, again, y equals x minus 1 squared, so you know what that looks like. Y equals x squared would just be here, so it's shifted to the right by 1 unit, so it's over here, okay. So it's definitely hitting the axis here. Now we've just got to think very carefully now about whether this graph is going to intersect here or not. And if we think in more detail about x minus 1 squared, well, when x equals 0, y equals 1, so actually it only gets, it intersects the other graph just here, and it's got a line of symmetry here as well, so it's also going to intersect the cosine graph over here. Okay, so we can complete it like this, and clearly, you know, this graph is now going increasing in both directions here forever, whereas this one is just oscillating. So these are the only intersections we get. So there must be 1, 2, 3, 4 roots of this equation. And I look back at my graph. This one has 2 roots, so it can't be that one. This one has 1, 2, 3, 4 roots, so that's a possibility. This one has 1, 2, 3, 4, 5, 6 roots by the looks of it, so can't be that one, and it must be this graph. Okay, there may be some other ways we could do this as well, possibly. I haven't thought about it really, but maybe, you know, differentiating, looking at turning points or something might be reasonable. I'm not really sure, but you know, we just want to find one way of doing it. So I would tend to start with the simplest things, which is to look for axis crossing points. If that didn't work, I would then maybe start thinking about turning points or something else. But you know, there are some. If you look back through the past papers, there are a lot of really good questions of this sort actually, where they ask you to consider different sorts of graphs, not always just graphs of functions as well. So I remember a good question where they ask you, I think you have to consider like sine x equals sine y or something like that. What does that graph look like? And it takes a bit of thought. So we've done the first half of the short answer questions there then, and I think that's a good point to pause. And we will look at the second half of those short answer questions in another video, and hopefully I'll get around to doing some of the longer answer questions as well.